Welcome to my channel, Cosmic Lullaby Channel, where relaxing stories and fascinating facts come together to help you unwind and fall asleep peacefully. In the silent, unending expanse of the cosmos, a question persists, one of the most profound and unsettling inquiries in the history of human thought. It is a question that challenges the very foundation of our identity, suggesting that the story of life on Earth may not have begun here at all. Could it be that our planet was not a cradle, but merely a destination? That the first infinitesimal spark of biology was a traveler, an alien seed carried across the unimaginable gulfs of interstellar space? This audacious concept is known as panspermia, a theory proposing that life is not a local phenomenon, but a cosmic one, and that our ancestral roots stretch far beyond Earth, into the deep and mysterious past of the galaxy itself. The implications are staggering. If true, it would mean we are all cosmic migrants, the descendants of an ancient lineage that predates our own world. It would reframe our entire understanding of evolution, theology, and our place in the universe, forcing a global reckoning with the idea that we are not alone, not because of intelligent visitors, but because life itself is a universal contagion. This is not merely a philosophical debate. It has become a new frontier in the silent geopolitical race for scientific dominance. The answer to this question holds the power to reshape nations' technological prestige and humanity's collective destiny. Over the course of this investigation, we will dissect the evidence for this extraordinary claim. We will explore the cosmic vehicles, the asteroids and comets that could serve as interplanetary vessels shielding fragile biology from the horrors of space. We will examine the data from decades of high-stakes laboratory experiments and orbital missions that have tested the absolute limits of life's endurance against the vacuum and lethal radiation of the cosmos. We will analyze the silent messengers that have reached our planet, meteorites fallen from the sky, carrying within them the complex organic molecules that form the very building blocks of life, asking a crucial question: are they simply raw materials, or are they clues to our true origin? Finally, we will confront what it would mean for humanity if the seeds of biology were not just scattered across our solar system, but sown throughout the entire Milky Way galaxy, a vast, interconnected ecosystem of worlds. The search for this truth is no longer confined to academic speculation. It is now the focus of billion-dollar space missions, a quiet but intense competition between global powers to retrieve the samples from distant worlds that could finally provide a verdict on our own solitude. The term panspermia, derived from the ancient Greek words pan, all, and sperma, seed, evokes a universe teeming with latent life. The idea, in its philosophical form, has ancient echoes, with thinkers like the Greek philosopher Anaxagoras in the 5th century BC pondering whether the seeds of life might drift eternally through the cosmos, settling where conditions were favorable. For millennia, it remained a poetic fancy. But in the early 1900s, at the dawn of a new scientific age, the concept was resurrected with empirical rigor by the Swedish chemist and Nobel laureate Svante Arrhenius. Arrhenius proposed what he termed radiopanspermia, a startlingly imaginative hypothesis suggesting that microscopic spores, light enough to escape a planet's atmosphere, could be pushed across the vast distances between star systems by the gentle but relentless pressure of starlight itself. The overall mood with a warm, friendly tone. These hardy biological seeds riding on waves of solar radiation like cosmic surfers, journeying for eons before perhaps finding a new, fertile world to colonize. The proposal was met with a mixture of fascination and deep skepticism. It was a powerfully poetic notion that resonated with a romantic view of the cosmos. Yet it was also profoundly disconcerting, suggesting that Earth was not a sealed and sacred cradle, but a porous system vulnerable to cosmic drift and biological contamination. The idea unsettled the scientific establishment of the time, which was firmly focused on a terrestrial origin for life. And it challenged the theological view of Earth as a uniquely divine creation. Throughout the turbulent 20th century, as humanity's reach extended into space, the theory of panspermia refused to disappear. Instead, it evolved, branching into new, more testable forms. The debate intensified when Francis Crick, the co-discoverer of the double helix structure of DNA, along with biochemist Leslie Orgel, took the idea a step further. In a provocative 1973 paper, they speculated about directed panspermia, the almost unthinkable possibility that life on Earth was not an accident but an intentional act, deliberately seeded by a distant, advanced extraterrestrial civilization. While they presented it as a thought experiment to challenge assumptions, it electrified the scientific community and blurred the line between mainstream science and speculative fiction. Today, the theory of panspermia continues to occupy a precarious position on the fringes of consensus science, but it is a fringe that is steadily being pulled closer to the mainstream. The overall Martian meteorite found in Antarctica, every organic molecule detected in an asteroid sample, and every extremophile discovered thriving in Earth's most hellish environments, the core tenets of the theory are being re-examined not as speculation, but as a set of difficult yet testable hypotheses. Modern scientific inquiry has revealed that panspermia is not a single monolithic theory, but rather a family of related concepts, each proposing a different mechanism for the transit of life. These can be understood as three distinct operational models, ranging from the physically plausible to the deeply provocative. The first, and by far the most grounded in observable physics, is known as lithopanspermia. This is the workhorse of the panspermia hypothesis, a scenario where life travels not as a naked spore, but as a stowaway, hidden deep within the heart of a rock. The process begins with a cataclysmic event. A large asteroid or comet slams into a life-bearing planet with unimaginable force. This impact ejects vast quantities of crustal material into space, some of which achieves escape velocity. Critically, not all this material is sterilized. In what physicists call spallation zones, fragments of rock can be blasted away from the impact site with surprisingly low heating and shock pressure, creating a window of opportunity for any embedded microbes to survive the violent launch. Protected from the vacuum and radiation of space by a natural shield of stone, these microscopic travelers could endure journeys lasting thousands or even millions of years before their rocky vessel is captured by the gravity of another world and crashes to the surface. This is not mere speculation. We have irrefutable proof that this interplanetary exchange occurs. Our museums house meteorites, such as the famous Allen Hills 8401, which we know through chemical analysis originated on Mars and landed here on Earth. The delivery system exists. The only remaining question is whether it has ever carried live cargo. The second variant is radiopanspermia, the original, more poetic vision conceived by Svante Arrhenius. In this model, individual bacterial spores or other microorganisms, being infinitesimally small and light, could be pushed out of a planet's upper atmosphere and propelled across interstellar distances by the sheer pressure of starlight. It is an elegant and romantic idea, life riding on beams of light across the galaxy. However, it faces a near insurmountable physical challenge, the lethal gauntlet of space. Without the thick shielding of a rock, a lone microbe would be directly exposed to a relentless storm of hard vacuum, extreme cold, and, most critically, a sterilizing bath of ultraviolet and cosmic radiation. Fragile organic molecules, including the DNA that carries life's code, would be shredded in relatively short order. While recent experiments on the International Space Station have proven that some hardy microbes can survive in open space for several years, this is a far cry from the millions of years required to traverse the gulf between star systems. Radiopanspermia, therefore, remains a compelling thought experiment, but is considered highly unlikely by the majority of the scientific community. The third and most controversial flavor is directed panspermia, a concept that ventures from astrophysics into the realm of geopolitics and philosophy. Championed as a thought experiment by Francis Crick and Leslie Orgel, it posits that life on Earth might have been deliberately seeded by an intelligent alien civilization. The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. This is not a theory of alien visitation, but of cosmic propagation, an ancient unknown actor sending out probes laden with microbial life to seed promising, sterile worlds. While most scientists categorize this as science fiction, its implications are profound, functioning as a kind of geopolitical ghost in the machine of astrobiology. The very possibility, however remote, forces us to confront the motives of unknown intelligences and the notion that our existence could be the result of a deliberate external strategy. But why should we dwell on these seemingly outlandish ideas at all? Isn't the study of life's chemistry here on Earth sufficient? The answer is no, because if any form of panspermia played a role in our origins, it fundamentally changes our entire conception of our place in the cosmos. First, it would radically redefine our ancestry. If life arrived here from elsewhere, then our biological lineage is not exclusively terrestrial. Our family tree would have roots that stretch beyond the formation of Earth itself, potentially back to an older Mars, a hidden ocean on an icy moon, or even a planet orbiting another star. This would mean that biology is not a local accident, but a galactic phenomenon, and that we are not just creatures of this world, but children of the cosmos. Second, it alters the odds of life's existence. If every habitable world must independently invent biology from scratch through the fiendishly complex process of abiogenesis, then life might be an exceedingly rare event. But if it can spread from world to world, it only needs to arise once in a given region of the galaxy. Subsequent worlds could receive a biological starter kit, inheriting the machinery of life rather than reinventing it. The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The universe flows through our world. If even the simplest microbes can survive that journey, then the barrier between here and out there is an illusion. Life may not be confined by the boundaries of planets, but may instead be a traveler on the cosmic currents, forever seeking new shores. Within the fiercely competitive and often unforgiving world of mainstream science, the theory of panspermia occupies a delicate and highly scrutinized position. It is not an idea that is widely accepted as the definitive explanation for life's origin on Earth, yet neither is it dismissed as mere fantasy. Instead, it is treated as a persistent, high-risk, high-reward possibility that demands rigorous, evidence-based testing. This intellectual balancing act creates a tense landscape where reputations can be made or broken. The scientific gatekeepers, the senior researchers, journal editors, and funding agencies draw a sharp distinction between the different versions of the theory. Lithopanspermia, the exchange of life via rocks, is now considered entirely plausible from a physics standpoint. The discovery of Martian meteorites on Earth provides undeniable proof of the transport mechanism. Sophisticated computer models run on supercomputers at institutions like NASA and the ESA have confirmed that microbes shielded deep within rock could, in principle, survive the triple gauntlet of ejection from a planetary impact, a long transit through space, and a fiery atmospheric entry. What remains the billion-dollar unknown is whether any organisms actually did make that journey successfully. The overall mood of missions like the Mars Sample Return. In stark contrast, radiopanspermia, while historically significant as Arrhenius's original vision, is far harder to support with modern data. The brutal physics of interstellar space work against it. The overwhelming exposure to solar and cosmic radiation, combined with the immense timescales required for travel between star systems, presents a seemingly fatal challenge for fragile biology. While orbital experiments have shown that some extremophiles can survive for years when shielded, these timeframes are trivial compared to the millions of years needed to cross the interstellar void. Directed panspermia remains the most speculative and is largely considered intellectual heresy within the scientific community. It crosses a critical line from testable astrophysics into untestable speculation about alien intent and sociology. In the absence of any evidence, it is a topic relegated to the domains of philosophy and science fiction, serving as a powerful narrative device but not a current scientific pursuit. This cautious, tiered approach is essential because the field is haunted by a history of sensationalist fringe claims. Time and again, announcements of alien microbes in meteorites or bizarre phenomena like the red rain in Kerala, India, have ignited media firestorms, only to collapse under rigorous scientific scrutiny. These episodes have left a legacy of skepticism, reinforcing a core principle of scientific inquiry, famously articulated by Carl Sagan: extraordinary claims require extraordinary evidence. A critical misconception that must be addressed is that panspermia is an attempt to replace the theory of abiogenesis, the natural origin of life from non-living chemistry. In reality, the two concepts are not competitors, they are partners in explaining the full story of life. Abiogenesis remains the foundational paradigm for understanding how life begins. Across the globe, in high-security labs, experiments relentlessly probe the central mystery. How did simple inorganic molecules on the early Earth assemble into complex, self-replicating systems? Panspermia does not eliminate this fundamental question, it simply relocates it. Think of it as tracing a great river back to its source. Abiogenesis is the search for the specific spring where chemistry first bubbled over into biology. Panspermia merely asks whether that spring was located here on Earth or on some other world, like a water-rich early Mars or an ocean moon. It doesn't remove the need for a spring, it just changes the cosmic address. In a fascinating twist, some theorists argue that panspermia could actually make the puzzle of abiogenesis easier to solve. If countless worlds across the galaxy, Mars, Europa, Enceladus, and billions of distant exoplanets were all running the same chemical experiment simultaneously, the statistical odds of it succeeding somewhere increase dramatically. Life might have emerged in many places, with only a few of those origins successfully spreading to neighboring worlds. In this grander vision, Earth is not a singular miraculous anomaly, but potentially just one successful node in a vast interconnected galactic network of biological attempts. This powerful synthesis keeps both of the ultimate questions alive and in play. First, how and where does life begin? And second, once it begins, how far can it travel? The answer to one may very well depend on the answer to the other. Now that we have established the operational framework of panspermia and its complex position within the scientific establishment, we must turn to the central question: what is the actual evidence? This is the critical juncture where the theory transitions from philosophical speculation into the high-stakes arena of testable empirical science. The case for panspermia is not built on a single definitive discovery, but on multiple converging lines of inquiry drawn from physics, biology, and chemistry. Each provides a crucial, albeit incomplete, piece of a much larger and more profound puzzle. The first and most concrete line of evidence is rooted in the brutal mechanics of astrophysics. We know with absolute certainty that catastrophic impacts on planets are violent enough to launch surface rock into interplanetary space. More importantly, we have tangible proof that these rocks can complete the journey between worlds. Our collections contain dozens of meteorites, like the famed Tissant meteorite that fell in Morocco in 2011, which chemical and isotopic analysis has unequivocally identified as originating from the planet Mars. These Martian rocks are not theoretical. They are physical artifacts of an interplanetary delivery service that has been operating for billions of years. If the vehicle exists, and we know it does, the most pressing question becomes whether it is capable of carrying life. The second line of evidence emerges from the astonishing resilience of biology itself. In the most extreme environments on Earth, from the crushing pressures of the Mariana Trench to the boiling acid hot springs of Yellowstone and the desiccated, radiation-blasted deserts of Antarctica, we find life. We have discovered a class of organisms known as extremophiles, which not only survive but thrive in conditions that would be instantly fatal to humans. Certain organisms, such as bacterial spores, lichens, and the nearly indestructible tardigrades, have demonstrated a shocking capacity to endure the hellscape of outer space. In a series of groundbreaking experiments conducted on platforms attached to the exterior of the International Space Station, these organisms have been left exposed to the raw vacuum, intense temperature swings, and unfiltered solar radiation for years at a time. The overall mood has been a revelation. While many perish, a significant number survive, demonstrating that biology is far tougher than we ever imagined. These survivors offer a compelling proof of concept that the transit phase of a panspermia journey, while brutal, may not be an absolute barrier to life. The third and perhaps most tantalizing line of evidence comes from the field of astrochemistry. For decades, scientists have analyzed meteorites that have fallen to Earth and have found them to be rich in the fundamental building blocks of life. Carbonaceous chondrites, like the Murchison meteorite, contain a stunning variety of organic molecules, including amino acids, sugars, and the nucleobases that form the rungs of the DNA ladder. For a long time, a lingering doubt persisted. Could these molecules simply be terrestrial contamination that infiltrated the rocks after they landed? That doubt was decisively erased by recent high-profile sample return missions. Japan's Hayabusa 2 mission to the asteroid Ryugu and NASA's OSIRIS-REx mission to the asteroid Bennu collected pristine material directly from the surface of these primitive bodies and returned it to Earth in sealed capsules. The analysis of these untainted samples was a watershed moment. They confirmed the presence of numerous organic molecules, including uracil, one of the 4 essential bases of RNA, and a host of amino acids. These missions proved beyond any reasonable doubt that space itself is a factory for the ingredients of life. While these are not signs of life itself, they demonstrate that the cosmos is pre-stocked with the necessary chemistry ready for delivery. These 3 pillars, a proven transport mechanism, the demonstrated toughness of life, and a universe rich in prebiotic ingredients, form the foundation of the modern panspermia hypothesis. Yet, they also illuminate the critical questions that remain unanswered. Can microbes truly survive the entire multi-stage journey? The violent ejection, the long radiation-soaked transit, and the fiery atmospheric entry? And if life did arrive from space, why has the search for extraterrestrial intelligence or even simple microbial life yielded only a profound silence? In the sections to come, we will deconstruct each stage of this cosmic journey, weighing the immense odds and exploring the cutting-edge experiments that may finally tell us how close or how far panspermia is from the truth. For lithopanspermia to be a viable theory, life must survive a three-act drama of unimaginable violence, a journey that begins with a cataclysmic launch. When a planet is struck by a large asteroid or comet, the energy released is apocalyptic, dwarfing the entire nuclear arsenal of Earth by orders of magnitude. The crust shatters, sending shock waves racing through the planet's lithosphere, and a plume of vaporized rock and debris is hurled into the upper atmosphere at speeds that defy comprehension. Most of this material, trapped by gravity, falls back in a fiery rain. But a small critical fraction crosses an invisible threshold, achieving escape velocity and being flung into the cold void of interplanetary space. For decades, it was assumed this process would be utterly sterilizing. Yet sophisticated modeling has revealed a crucial loophole in the physics of hypervelocity impacts. In the upper layers of rock near the impact zone, in what are known as spallation windows, fragments can be blasted free with surprisingly low levels of heating and shock pressure. If the conditions of the impact angle, velocity, and rock composition are just right, a piece of stone can be ejected into orbit while its interior remains remarkably cool, shielding any microbial life buried within. For biology, this narrow path is everything. The overall mood of impact and the rock is vaporized into plasma. Too deep and it never leaves the ground. But in that delicate balance lies a window of opportunity, a chance for microscopic organisms to hitch a ride to the stars. We know this ballistic exchange is not a mere theory because we are the recipients of it. Martian meteorites found in the ice fields of Antarctica are tangible proof that material has traveled from the red planet to our own, completing a journey of millions of kilometers. The transport system is real. The question that haunts astrobiologists is whether it has ever delivered living passengers. Once freed from its home world, the rock fragment and its hidden cargo enter the second act, a long, silent transit through an environment more hostile than any on Earth. The absolute vacuum of space instantly strips away any remnant atmosphere and boils off water. Temperatures plummet to hundreds of degrees below zero, locking any biological processes in a deep freeze. And then there is the most relentless and insidious killer, radiation. Unfiltered radiation from the sun, along with high-energy cosmic rays, protons, and heavy nuclei accelerated to near the speed of light by distant supernovae, bombard every exposed surface. For unprotected organic molecules, this is an instant death sentence. Ultraviolet light slices through chemical bonds in seconds, while cosmic rays methodically grind complex structures like DNA into useless fragments over time. Yet, inside a sufficient shield of rock, the calculus of survival changes dramatically. Just a few centimeters of stone can act as a natural sarcophagus, absorbing the worst of the radiation and reducing the dose to survivable levels. Bacterial spores, already in a state of deep dormancy with their metabolism frozen and their DNA tightly coiled, could potentially last for astonishing spans if they remain entombed within this rocky shelter. This is not speculation. In a series of critical experiments on the International Space Station, spores exposed on the outside of the facility survived for years. Deep in the core of a meteorite, shielded from the direct onslaught, survival times could theoretically stretch into the millions of years needed for an interplanetary journey. The transit phase is a brutal war of attrition, but it is not automatically fatal. Life's toughest survivors could, in principle, drift in a silent, suspended animation, waiting for the final act. The fragment's cosmic odyssey is not complete until it encounters another world, but this final stage, atmospheric entry, is arguably the most perilous of all. Slamming into the upper atmosphere at speeds of tens of kilometers per second, the rock compresses the air in front of it, generating a superheated fireball with temperatures exceeding those on the surface of the sun. The exterior of the meteorite melts and vaporizes in a process called ablation, creating the brilliant streak of a meteor across the sky. Yet, once again, the principle of shielding is paramount. A sufficiently large meteorite functions as its own natural heat shield, much like the ablative shields on the Apollo command modules. While its surface incinerates, the intense heat doesn't have time to penetrate to the core, which can remain close to the freezing temperatures of deep space. If any microbes were buried deep inside, they could pass through this fiery crucible completely untouched. This crucial concept has been validated by direct experimentation. In one stunning test, bacterial spores were sealed inside artificial meteorites, attached to the outside of an orbital capsule, and subjected to a real fiery re-entry. Upon recovery, the spores were found to be viable. The final hurdle is the landing itself. A catastrophic impact could sterilize the payload, but smaller fragments, slowed by their passage through the atmosphere, can fall at terminal velocity, landing with no more force than a dropped stone. The odds of any single microbe completing this entire three-act journey are infinitesimally small. But across the geological timescales of the solar system, with countless impacts creating a constant exchange of material, even the slimmest odds become statistically meaningful. Arrival is a gauntlet, but physics shows us it is not an impossible one. The overall movement of a rock flung into space is, in reality, anything but. The solar system is not an empty, chaotic void, but a complex, dynamic machine governed by invisible forces. Its architecture is defined by gravitational currents, resonances, and orbital corridors that create what scientists call dynamical highways. These are preferential pathways that guide the movement of matter between planets. When a rock is ejected from a world like Mars, its path is not left to chance. It is immediately captured by this gravitational web. The immense gravity of planets, particularly the colossal influence of Jupiter, acts as a cosmic shepherd, nudging, deflecting, and steering these fragments into new orbits. An object can be flung out of the solar system entirely, sent on a lonely journey into the interstellar dark, or, critically, it can be nudged inward, onto a trajectory that eventually crosses the path of Earth. This understanding transforms our view of interplanetary exchange from a game of random chance into a predictable, albeit complex, system of transport logistics. Crucially, computer simulations modeling these highways have yielded a startling result. While most journeys between Mars and Earth take millions of years, a time frame likely fatal to any microbial passenger, a small but significant fraction of ejected rocks can make the trip with astonishing speed. These are the express lanes of the dynamical highway system. A tiny percentage of fragments can arrive in just a few thousand years, and a few rare lucky travelers can complete the journey in a matter of decades. These rare, fast routes are of paramount importance to the panspermia hypothesis. A journey lasting only 20 or 30 years dramatically shortens the exposure to cosmic radiation, keeping the cumulative damage within a range that hardy microbes might realistically be able to withstand. The overall mood of these rapid transit paths means that the window for survival, while narrow, is real. It provides a physical mechanism that directly addresses one of the most significant objections to the theory, the seemingly insurmountable timescale of space travel. The solar system, it turns out, is a far more interconnected and efficient delivery system than we ever imagined. This paradigm of cosmic interconnectedness was shattered and radically expanded in 2017. Astronomers at the Halakala Observatory in Hawaii detected something unprecedented: a strange cigar-shaped object tumbling end over end as it sped through our solar system. It was moving too fast to be bound by our sun's gravity, revealing its true nature. It was a visitor from another star system. Named Oumuamua, Hawaiian for a messenger from afar, it was the first interstellar object ever directly observed. Just 2 years later, a second visitor, a more conventional-looking comet named Borisov, confirmed that Oumuamua was not a once-in-a-lifetime fluke. These discoveries fundamentally changed the calculus of panspermia. Interstellar objects are not rare, they are common, passing through our solar system with a frequency that stunned the astronomical community. Current estimates suggest that trillions upon trillions of such objects are wandering the dark gulfs between the stars, acting as potential couriers linking planetary systems across the entire galaxy. If even a tiny fraction of these interstellar travelers carry the chemical precursors of life, or perhaps even dormant microbes shielded within ice or rock, then the exchange of biological material may not be limited to our solar system. It could be a galactic process. This new reality, one of a galaxy teeming with physical couriers, stands in stark contrast to the earliest and most romantic vision of panspermia, radiopanspermia. The overall mood of panspermia, envisioned by Arrhenius over a century ago, life travels not in the belly of a rock, but on the open waves of starlight. The pressure of photons radiating from a star, he argued, could be enough to push the tiniest bacterial spores out of a star system and into the interstellar void. On paper, the physics is sound. Radiation does exert pressure. But biology is not paper. A lone spore, naked and exposed to the full fury of space, faces a gauntlet of sterilization that is swift and absolute. A direct bath of hard ultraviolet radiation would shred its DNA in mere hours. A relentless bombardment by cosmic rays would methodically break its chemical bonds over the long journey. Laboratory experiments have consistently supported this grim assessment. While some microbes can survive for years in shielded crevices on the International Space Station, none have shown the capacity to endure the millions of years needed for an interstellar voyage while fully exposed. Shielding the spore within a grain of dust or ice would certainly help, but at that point, the mechanism becomes a form of microlithopanspermia, relying on a physical shield rather than the gentle pressure of light. Radiopanspermia, therefore, remains a poetic and historically important thought experiment, but it has been superseded by the far more robust and physically plausible model of life as a hardened traveler, entombed in stone, navigating the cosmic highways of the galaxy. To survive the cosmic gauntlet, life would need a secret weapon, a biological trick evolved not for space, but for enduring catastrophe on Earth. That trick is dormancy. When faced with an existential threat, a frozen wasteland, a boiling desert, a lethal dose of radiation, certain organisms do not fight back. They simply pause. The overall mood is a state of suspended animation so profound that it blurs the line between life and death. The most extreme masters of this art are bacterial spores. Encased in a tough, multi-layered protein shell with their precious DNA tightly wound and their internal water content reduced to almost nothing, they become microscopic time capsules. Heat, cold, desiccation, and even radiation inflict damage at a glacial pace when the machinery of life is frozen solid. This is not a hypothetical state. Scientists have successfully revived bacterial spores that were trapped for millions of years within ancient salt crystals, still viable after a geological slumber that began when our own ancestors were just beginning to walk upright. This incredible endurance is not limited to microbes. The plant kingdom has evolved a parallel marvel of engineering, the seed. Though far more complex than a simple spore, many plants package their embryos in biological armor, providing nourishment and protection designed to ride out winters, droughts, or even the cleansing fire of a forest blaze. In a now famous experiment, a lotus seed retrieved from a dry lake bed in China was successfully coaxed into germinating after more than 1,000 years of dormancy. These are not adaptations for space travel, but they are a powerful demonstration of biology's hidden toughness. If an organism can survive entombment in salt for 250 million years, it is not a great leap to imagine it could also survive entombment in rock during a long, frozen voyage through space. Dormancy does not offer a guarantee of survival, but it radically stretches the odds. The champions of this silent waiting game are a constant reminder that life has already solved the problem of outlasting the apocalypse. It simply waits for conditions to improve, whether that takes a season or a geologic epoch. Speculation is one thing, but empirical data is another. To move panspermia from theory to science, researchers had to test these limits directly in the only laboratory that mattered, space itself. In a series of audacious experiments, scientists have carried Earth's hardiest organisms to the International Space Station and deliberately left them outside, exposed to the raw, unfiltered environment of low Earth orbit. These missions, known collectively as EXPOSE, placed a curated gallery of microbes, lichens, algae, and even simple animals on external platforms for months or years at a time, subjecting them to a trial by cosmic fire. The results were both sobering and astonishing. As expected, many organisms died quickly when exposed to the full, unfiltered glare of solar ultraviolet radiation. Yet, when provided with even the slightest shade, or when tucked into tiny simulated rock crevices, some survived for years. Bacterial spores, sealed within these artificial niches, endured up to 6 years in orbit and were still viable upon their return. Even complex organisms like lichens, scraped from the sides of rocks on Earth, were able to resume photosynthesis after being exposed for nearly 2 years outside the station. The Japanese-led Tenpapo experiment expanded on this work, focusing specifically on the hypothesis that microbes might hitchhike on particles of cosmic dust. For 3 years, microbial samples were mounted on the outside of the Kibo module, some bare and some protected by thin layers, to measure their degradation over time. When retrieved, some of the shielded colonies remained viable, demonstrating that even a thin layer of dust or stone could provide sufficient protection for an interplanetary journey. What these orbital trials reveal is not a simple yes or no, but a gradient of possibility. Bare, unprotected life is shredded by solar radiation in weeks. But hidden life, shielded in even the most minimal shelters, can endure for years, a timescale more than long enough for the fastest transfers between nearby planets, especially along the rapid corridors of the dynamical highways. No single experiment has yet proven that life could survive the millions of years required for an interstellar journey. But the very fact that survival is measurable at all, even across years of exposure in low Earth orbit, is what has transformed panspermia from a fanciful notion into a legitimate, testable scientific hypothesis. These missions show us that biology, though fragile, possesses an unexpected and stubborn resilience when given even the thinnest of refuges against the storm of the cosmos. For sheer stubborn refusal to die, few creatures in the known biological universe can rival the tardigrade. These microscopic eight-legged animals, often affectionately called water bears for their endearing, lumbering gait, are the undisputed champions of survival. When conditions become dire, the tardigrade does not flee or fight. It enters a state of profound cryptobiosis, known as a ton, in which it retracts its legs, expels nearly all the water from its body, and shuts down its metabolism to less than 0.01% of normal. In this state, it is less an animal and more a piece of living glass, a biological statue capable of enduring conditions that would annihilate almost any other life form. The overall mood of life's ability intensive, perfect for bedtime reading and space narration. They can withstand temperatures from near absolute zero to well above the boiling point of water, pressures 6 times greater than those in the deepest ocean trench, and doses of radiation hundreds of times higher than the lethal limit for humans. For decades, their resilience was the stuff of laboratory legend. But in 2007, scientists decided to subject this creature to the ultimate test, launching them into open space on the European Space Agency's Photon M3 mission. For 10 days, groups of tardigrades were exposed to the hard vacuum and unfiltered solar radiation of Earth orbit. Many perished, as expected. But astonishingly, some survived the ordeal, later rehydrating and successfully reproducing back on Earth. This was a landmark moment in astrobiology, the first time a multicellular animal had ever endured direct, unprotected exposure to the horrors of space and lived to tell the tale. It is crucial to understand that tardigrades themselves are not serious candidates for cosmic hitchhikers. Their survival times in open space are measured in days, a mere blink of an eye compared to the millennia required for even the fastest interplanetary journeys. However, their true significance is not as passengers, but as boundary markers. They serve as a stunning, living proof of concept, a biological benchmark that fundamentally recalibrates our understanding of what is possible. If an animal, a complex organism with specialized tissues and organ systems, can survive even 10 days in the raw vacuum and radiation of space, then it is no longer unreasonable to hypothesize that simpler, far hardier life forms, like bacterial spores, already adapted for millennia of dormancy, could survive vastly longer when protected deep inside a rock. The tardigrade forces us to abandon our terrestrial biases about life's fragility. It is a powerful reminder that nature has already engineered solutions to problems of survival that seem insurmountable to us. Life does not always collapse under stress. Sometimes it simply contracts, waits, and emerges again when the storm has passed. However, surviving the passive state of space transit is only one part of the challenge. For panspermia to work, life must also endure the 2 moments of extreme kinetic violence that bookend the journey, the launch and the landing. Leaving a planet via an asteroid impact is not a gentle ascent. It is an act of unimaginable explosive force. A rock blasted into space experiences crushing accelerations and titanic shock pressures that can shatter crystalline structures and pulverize organic matter. To test whether life could withstand this, scientists have recreated the physics of impact in their laboratories. Using powerful gas guns, they have fired high-velocity projectiles into rock samples seeded with microbial spores, subjecting them to accelerations tens of thousands of times Earth's gravity. The results were telling. The outer layers of the samples were, as expected, completely sterilized. But deep within the microscopic cracks and pores of the rock, a fraction of the spores survived, their tough outer shells absorbing the lethal shockwave. Re-entry is the other crucible. A meteorite blazing through the atmosphere becomes a molten fireball. Yet, experiments that have embedded spores within heat-shielding materials on orbital capsules have shown that they can survive the fiery descent, emerging intact after their journey. Other tests have placed spores inside artificial meteorites and cooked them in laboratory furnaces that simulate the thermal profile of atmospheric entry, again with positive results. These experiments collectively point to the existence of a narrow but very real survivability window. Not every microbe would make it, in fact, not even most. The vast majority with a warm, friendly tone. For years, space is a beautiful place. But across billions of years, with countless impact events on countless worlds, even an exceptionally rare survival rate adds up. Biology, and indeed panspermia, does not require certainty. It only needs possibility, repeated often enough over the vastness of geologic time. Shock and heat are formidable barriers that dramatically reduce the odds, but they do not, as these experiments prove, reduce them to zero. While the violent bookends of launch and landing present acute, momentary threats, the true, insidious enemy of panspermia is the journey itself. The long transit through interplanetary space is a war of attrition fought against an invisible and relentless foe. For any organism, no matter how deeply entombed in rock, the voyage is a slow, agonizing bath in high-energy particles that methodically dismantle the very blueprint of life. The threat is not one of instant death, but of a gradual, cumulative decay, a cosmic rust that scrambles genetic information beyond any hope of repair. There are two primary forms of this assault. The first is solar radiation, particularly ultraviolet light, which, while easily blocked by even a thin layer of rock, is absolutely lethal to any exposed surface. The second and far more pervasive threat comes from galactic cosmic rays. These are the nuclei of atoms, mostly protons, accelerated to nearly the speed of light by cataclysmic events like supernova, exploding stars halfway across the galaxy. They are the universe's stray bullets, and they travel with such incredible energy that they can penetrate meters of solid rock, slicing through molecules and shattering DNA strands like a subatomic sandblaster. Over thousands or millions of years, the damage from these constant microscopic impacts mounts, causing mutations to accumulate until the organism's genetic code becomes an unreadable, garbled mess. Yet, to assume this is an automatic death sentence is to underestimate the sheer ingenuity of biology, which has spent billions of years evolving sophisticated countermeasures against radiation damage here on Earth. Life is not a passive victim. Spores, for instance, don't just go dormant, they actively prepare for disaster. They contain specialized proteins that physically bind to DNA, acting as molecular shields that stabilize the delicate helix and protect it from breaking apart under stress. But the most astonishing defense is not prevention, but repair. Some microbes possess extraordinarily efficient repair systems, molecular machines that can actively patrol the genome, identify breaks, and stitch the strands back together when conditions improve and the organism reawakens. The undoubted master of this genetic self-repair is a bacterium named Deinococcus radiogerans. Nicknamed Conan the Bacterium by scientists, this organism can withstand doses of radiation thousands of times greater than the lethal limit for humans. Its secret is not a magical shield, but an unparalleled DNA repair kit. Even after its genome has been shattered into hundreds of fragments by radiation, its enzymes can methodically reassemble the pieces in the correct order, effectively bringing its genetic code back from the dead. This incredible biological resilience reframes the entire problem. The survival of a cosmic traveler is not a simple matter of endurance. It is a high-stakes race between the pace of radiation damage and the speed of interplanetary transit. The key variable, therefore, is time. If a rock fragment is fortunate enough to catch a ride on one of the fast, dynamical highways and complete its journey from Mars to Earth in a few decades or centuries, the cumulative radiation dose remains within a range that an organism like Deinococcus radiogurans could plausibly repair. The journey would be damaging, but not necessarily fatal. However, if the journey stretches on for millions of years, as most do, the burden of mutations becomes overwhelming. Even the most robust repair systems are eventually defeated by the sheer volume of damage. The organism's genetic information would degrade past a point of no return, its half-life exceeded many times over. The average case for panspermia is therefore grim. But the theory doesn't depend on the average case, it depends on the exceptions. The existence of those rare, rapid transit routes is what matters most. Survival hinges less on biological perfection than on a cosmic lottery. Whether the biological time budget, set by the limits of DNA repair, can outlast the duration of the cosmic journey. Time is the ultimate filter. But as the physics of the solar system shows, it is not an absolute barrier. The statistics of interplanetary transit overlap just enough with the astonishing resilience of biology to keep the hypothesis alive. As scientists have delved deeper into the mechanics of panspermia and the astonishing resilience of microbial life, a sobering and profound realization has emerged, casting a long shadow over humanity's own exploration of the cosmos. If life can indeed survive the rigors of space travel, then our own robotic emissaries, the landers, rovers, and probes we send to other worlds, could unwittingly become the very agents of the phenomenon we are trying to study. The overall mood of forward contamination, the accidental introduction of Earth microbes to potentially habitable environments like Mars or the ocean moons of Jupiter and Saturn. A single stowaway bacterium from a clean room in Pasadena, surviving the journey and finding a niche on Mars, could contaminate an entire world, irrevocably corrupting the pristine environment we hope to study for signs of native life. It would be the ultimate scientific tragedy to travel hundreds of millions of kilometers in search of alien life, only to find our own reflection staring back at us. This is no longer a theoretical concern. It is a central operational challenge that governs the design and execution of every major interplanetary mission. This profound risk has given rise to the rigorous and expensive international discipline of planetary protection. It is a set of strict protocols enforced by space agencies like NASA and the ESA, designed to prevent biological cross-contamination between Earth and other celestial bodies. Spacecraft destined for worlds deemed potentially habitable undergo a painstaking process of sterilization. They are assembled in ultra-clean rooms where the air is filtered to a higher standard than in a surgical operating theater. Components are baked in ovens at high temperatures, blasted with radiation, and wiped down with powerful chemicals to minimize the microbial bioburden. These procedures are not perfect. No sterilization is absolute. The goal is not to achieve perfect sterility, which is impossible, but to reduce the probability of contamination to an acceptably low level. This reflects how seriously the scientific community takes the possibility of interplanetary contamination, an implicit acknowledgement that the core tenets of panspermia are plausible enough to warrant extreme precaution.
The ethics of planetary protection extend in the other direction as well, in a concept known as back contamination.
If we someday succeed in bringing samples back from Mars or Europa, we must treat them as potentially hazardous until proven otherwise. The protocols for a Mars sample return mission, for instance, are being designed with a level of biosecurity that rivals the most secure labs for studying deadly pathogens on Earth. The return samples will be quarantined in a specialized Biohazard Level 4 (BSL-4) facility, handled exclusively by robotic systems to ensure they never come into contact with Earth's biosphere. The scenario of an invasive Martian microbe wreaking havoc on terrestrial ecosystems is a staple of science fiction, but it is a remote possibility that is taken with the utmost seriousness by mission planners. Whether or not natural panspermia has ever occurred in the solar system's past, our own technological advancement has created the very real possibility of an artificial and potentially catastrophic panspermia event. Our relentless drive to explore forces us to confront this new reality. We have become the potential couriers. This responsibility changes the very nature of space exploration, transforming it from a pure act of discovery into one that must be balanced with a profound sense of custodial duty. Curiosity, the driving force of science, must now walk hand in hand with a caution born from the understanding that life, once established, is a remarkably persistent and potentially invasive force. The prime directive of science fiction has become a practical, ethical, and geopolitical reality. Every single day, our planet is under a constant, silent bombardment from the cosmos. This is not the stuff of disaster films, but a quiet, continuous rain of extraterrestrial material that has been falling since the Earth first formed. The overall mood is utterly invisible. Microscopic grains of dust that burn up harmlessly in the upper atmosphere, creating the fleeting beauty of a shooting star. But larger pieces survive the fiery descent, landing as meteorites on the ice fields of Antarctica, the deserts of Africa, and the farmlands of the world. By conservative estimates, tens of thousands of tons of this material fall upon our planet each year, a steady influx from the wider solar system. For most of human history, these falling rocks were seen as omens or curiosities. Today, we understand them as something far more profound. They are messengers. Each one is a physical sample, a time capsule carrying chemical secrets from the dawn of the solar system, and potentially clues to the origin of life itself. These messengers arrive in many forms. Some are dense, metallic chunks of iron and nickel, the shattered hearts of ancient asteroids forged in the heat of planetary formation. Others are stony, with textures that resemble terrestrial volcanic rock. But a rare and precious subset, the carbonaceous chondrites, are the holy grail for astrobiologists. These rocks are fundamentally different. They are dark, fragile, and rich in the one element that defines life as we know it: carbon. They are cosmic fossils, remnants of the primitive solar nebula that have remained largely unchanged for 4.5 billion years. What makes these meteorites, and indeed all meteorites, crucial to the panspermia hypothesis is their remarkable ability to function as natural delivery capsules. As they blaze through the atmosphere at hypersonic speeds, their outer layers melt and vaporize, creating a superheated shield of plasma. But this process of ablation happens so quickly that the intense heat does not have time to penetrate to the core. The overall mood of deep space can remain close to the absolute cold of deep space, perfectly preserving its delicate chemical cargo during the fiery plunge. They are not just falling rocks, they are nature's own sample return missions, delivering pristine chemistry from across the solar system, free of charge. For decades, this was a tantalizing theory. But in September of 1969, the theory became an electrifying reality. A brilliant fireball lit up the night sky above the small town of Murchison, Australia, before exploding into thousands of fragments that rained down across the countryside. Locals, alerted to the scientific importance of the event, quickly gathered the blackened, carbon-rich stones. Because they were collected so soon after falling, the Murchison meteorite was remarkably fresh, largely free from the terrestrial contamination that plagues older finds. What chemists discovered inside would rewrite the textbooks on the origin of life. The Murchison meteorite was a chemical treasure trove. Within its dark matrix, scientists identified over 70 different types of amino acids, the fundamental building blocks of proteins, the very machinery of life. Many of these were the same 20 amino acids used by all living things on Earth. But critically, many others were exotic, alien forms not found in terrestrial biology. This was the smoking gun. The presence of these non-terrestrial forms proved that the amino acids were not earthly contamination. They had formed spontaneously in the cold, sterile environment of space, on the parent asteroid from which the meteorite came. But the most stunning discovery was yet to come. It involved a subtle property of chemistry known as chirality. Like human hands, many organic molecules can exist in two mirror image forms, a left-handed L version and a right-handed D version. Non-biological chemistry produces them in a perfectly equal 50-50 mix. The overall mood, relaxed, filled almost exclusively from left-handed amino acids. This is called homochirality. When scientists analyzed the Murchison amino acids, they found a slight but statistically significant excess of the left-handed versions. The implication was a bombshell that sent shockwaves through the scientific community. It suggested that some process in the cosmos, perhaps the interaction of molecules with polarized starlight in the interstellar medium, had already biased the chemical deck in favor of the very configuration that life on Earth would eventually adopt. The Murchison meteorite was more than just a delivery of raw materials. It was a delivery of biased materials. It demonstrated that meteorites are not sterile lumps of rock, but dynamic chemical laboratories carrying a toolkit for life, pre-sorted and ready for assembly. Whether or not a living microbe ever hitched a ride, this discovery proved that the universe was already delivering chemistry that pointed the way toward biology, making Murchison a cornerstone in the modern evidence-based case for panspermia. The bombshell discovery within the Murchison meteorite was not an isolated event. It was the beginning of a revolution. It opened the floodgates, and soon other fallen messengers began to yield their own tantalizing secrets, each one adding a new layer of complexity to the story of cosmic chemistry. In the year 2000, a brilliant fireball disintegrated over the frozen expanse of Tagish Lake in Canada, scattering dark, carbon-rich fragments across the pristine ice. Because they were collected quickly from a frozen environment, the Tagish Lake samples were exceptionally well preserved, offering an almost unblemished snapshot of their parent body's chemistry. Analysis revealed a suite of organic compounds, but its composition was strikingly different from Murchison's. This was a crucial finding. It demonstrated that the cosmic factory for life's ingredients wasn't a monolithic assembly line producing a single product. Instead, different asteroids throughout the solar system were brewing their own unique varieties of organic molecules, creating a rich and diverse chemical inventory that was available for delivery to the early planets. The Orgel meteorite, an even older find that fell in France in 1864, further reinforced this narrative.
Though this fragile carbonaceous chondrite quickly crumbled, its chemistry was undeniable, carrying a distinct suite of building blocks that blurred the line between inanimate geology and the precursors of biology. Together, these silent stones painted a radical new picture of the early solar system. Organics were not a rare fluke. They were widespread, a recurring theme in the chemistry of primitive bodies. Each meteorite that fell was another data point, a glimpse into the vast library of prebiotic chemistry scattered throughout our cosmic neighborhood. A chemistry that could have seeded and primed the early Earth, providing a rich inventory of parts for the first biological systems to assemble.
The overall mood. These fallen meteorites carried an inescapable fatal flaw: the problem of contamination. From the moment a meteorite enters our atmosphere, it is under assault by Earth's biosphere. Air, water, bacteria, and fungi quickly infiltrate the fragile rock, leaving scientists with the maddeningly difficult task of distinguishing what is truly extraterrestrial from what is merely a terrestrial stowaway. This persistent doubt has haunted meteorite studies for a century, allowing skeptics to cast a shadow over even the most compelling findings. To truly settle the question, science needed to bypass Earth's contaminating influence entirely. It needed to go to the source. This imperative gave rise to one of the most ambitious and technologically demanding new chapters in the space race: the era of the asteroid sample return mission. These missions represent a quantum leap in the search for our origins. By traveling hundreds of millions of kilometers to an asteroid, collecting a pristine sample of its surface, and returning it to Earth in a hermetically sealed capsule, scientists could finally analyze material that has never been touched by Earth's biosphere. Japan's Hayabusa 2 mission was the first to achieve this with breathtaking success. In 2018, it arrived at Ryugu, a small, diamond-shaped, carbon-rich asteroid. In a series of daring maneuvers, the spacecraft fired a small projectile into the surface, collected the plume of ejected debris, and then began its long journey home. When the capsule was opened in a secure lab in 2020, the dark grains inside contained a scientific revelation. Not only did they hold a variety of amino acids, but for the first time, scientists confirmed the presence of uracil, one of the 4 essential nucleobases that make up RNA, a molecule many believe was a precursor to DNA. The overall mood, or vitamin B3, a crucial component for metabolic processes in all known life. This was direct, irrefutable proof that the fundamental ingredients for both genetic material and metabolism exist on asteroids. NASA's OSIRIS-REx mission to the asteroid Bennu took this a step further. When its samples were returned to Earth in 2023, the initial analysis was even more stunning. The Bennu rubble was found to be rich in both carbon and water, and contained an unexpected bounty of magnesium-sodium phosphates. This discovery was electrifying. Phosphate is the P in ATP, the molecule that provides energy to our cells. It forms the structural backbone of both DNA and RNA and is essential for building cell membranes. Its presence in the pristine Bennu sample was another critical piece of the puzzle, suggesting that even the most fundamental components of life's machinery are not exclusive to Earth, but are forged in the chemistry of primitive asteroids. Together, the missions to Ryugu and Bennu represent a paradigm shift. They have provided the cleanest, most unambiguous evidence to date that the ingredients for biology are not only present, but widespread throughout the solar system. While they do not prove that living organisms traveled through space, they prove, beyond any doubt, that the chemistry for life did.
With every pristine sample returned, the line between Earth's biology and the chemistry of the wider cosmos becomes ever thinner, suggesting that our planet was not an isolated island, but a fertile shore lapped by a cosmic ocean rich with the potential for life.
The overall mood of panspermia has always raised a far more daring and profound possibility. Exchange not just between neighboring planets, but between the stars themselves. For centuries, this was the exclusive domain of pure speculation, a concept so vast it seemed untestable. The solar system was seen as a gravitational island, isolated from its galactic neighbors by an ocean of empty space so immense that crossing it was deemed a near impossibility. But this foundational assumption of cosmic isolation was shattered in 2017. Astronomers detected an object moving through our system on a trajectory so strange and at a velocity so high that it could only have one origin: interstellar space. It was Oumuamua, the first known visitor from another star system. Its bizarre, elongated shape and tumbling motion defied easy classification, and its discovery sent a shockwave through the global scientific community. This was a form of first contact, not with an intelligent civilization, but with a physical piece of another solar system's history, a messenger from a distant, unknown shore. The profound implications of Oumuamua were still being debated when, just 2 years later, a second interstellar traveler, Comet Borisov, was spotted. Unlike its strange predecessor, Borisov looked and behaved like a classic comet, complete with a gaseous tail. But its trajectory was, once again, unambiguously interstellar. The arrival of a second visitor in such a short time frame obliterated the idea that such events were once-in-a-civilization flukes. It was a paradigm-shifting revelation. Interstellar objects are not rare, they are common. The overall mood of science, with a warm, friendly tone, now suggests a stunning reality. A constant, steady stream of these objects is likely passing through our solar system every single year, most too small and fast to be detected. The galaxy, it turns out, is not a collection of isolated islands, but a dynamic, interconnected system constantly exchanging material. It is estimated that trillions of these cosmic vagabonds are adrift in the void between the stars, acting as a vast galactic courier service. This discovery fundamentally alters the potential scale of panspermia, elevating it from a local solar system level process to a potentially galactic one. This new reality immediately forces a critical question. What kind of cargo could these interstellar couriers be carrying? The first and most conservative answer is chemistry. Based on everything we know about the formation of stars and planets, it is almost certain that these objects carry the same raw materials for life that we find in our own system. The spectral analysis of Comet Borisov confirmed this, revealing a coma rich in carbon-based compounds, a chemical signature consistent with the organic-rich comets native to our own solar system. This implies that the building blocks of life, amino acids, nucleobases, phosphates, are likely not unique to our corner of the cosmos, but are ubiquitous, universal ingredients forged in the clouds of gas and dust from which all stars are born. But this leads to the far more provocative question: could they carry not just the ingredients, but finished, living organisms? Here, the odds become astronomically longer. The journey between stars takes not thousands, but millions of years. The exposure to the relentless bath of galactic cosmic radiation is far more intense and prolonged than any interplanetary trip. The overall mood of a dormant microbe across such an immense gulf of time and space remains far less likely. However, it cannot be dismissed outright.
If a viable microbe were shielded deep within the core of a sufficiently large, rocky, or ice-rich object, it might just be possible. The greater significance of Oumuamua and Borisov, therefore, lies not in proving interstellar panspermia, but in proving that the mechanism for it exists. The galaxy is far more interconnected than we ever imagined. Over the course of billions of years, it is a near certainty that materials have been exchanged not just within solar systems, but between them. Even if living organisms cannot survive the journey, the chemistry for life most certainly can. Every interstellar object that silently slips through our solar system is a reminder that the grand experiment of prebiotic chemistry is not confined to our neighborhood. It is a galactic process, playing out across billions of star systems, potentially creating a shared chemical heritage that makes the universe as a whole a more fertile and promising place for life to emerge. Of all the potential avenues for life's exchange within our solar system, one relationship stands out with such startling clarity that it has become the central focus, the ground zero, in the scientific and geopolitical quest for extraterrestrial life. The ancient, dynamic connection between Earth and Mars. These two worlds are more than just neighbors. They are siblings, born from the same protoplanetary dust cloud, occupying similar orbits, and, for a time, sharing remarkably similar early histories. The evidence suggests that billions of years ago, Mars was a far more hospitable world, with a thicker atmosphere, flowing rivers, and potentially vast oceans. The overall mood of life long before Earth had fully cooled from its violent formation. This proximity and shared history make the exchange of material between them not just a possibility, but a geological inevitability. For billions of years, asteroid and comet impacts have bombarded both planets, blasting trillions of tons of rock into space and creating a constant two-way traffic of debris between them. The evidence for this interplanetary highway is not based on computer models alone. It is tangible, physical, and sitting in our museums. We have in our possession meteorites found on Earth that we know with absolute certainty came from Mars. These are not ambiguous rocks. They are identifiable by their unique isotopic fingerprints. The chemical composition of tiny bubbles of gas trapped within their crystalline structure perfectly matches the atmospheric composition of Mars as measured directly by the Viking landers in the 1970s. This is the ultimate return-to-sender address, an undeniable link proving that rocks can be ejected from Mars, travel millions of kilometers through the hostile vacuum of space, and land here on our world. The reverse is also true. The same impact physics dictates that Earth material has, over the eons, been blasted into space and has almost certainly landed on Mars. The profound implications of this two-way street cannot be overstated. It raises one of the most fundamental questions about our own identity. If life did arise on Mars first, in its warmer, wetter past, it could have easily traveled to a younger Earth, seeding our world with Martian microbes. If this is the case, we are all the descendants of Martians. This is not science fiction. It is a plausible, testable scientific hypothesis. The overall mood of planetary seeding lies in the efficiency and speed of the transit. While many rocks would wander the solar system for millions of years, simulations of celestial mechanics show that some fragments can make the journey astonishingly fast. A small but significant fraction can arrive in as little as 20 years after being ejected, a time frame well within the survival limits of hardy, dormant organisms shielded deep within the rock. These fast-track deliveries are crucial, as they provide a direct, plausible mechanism for interplanetary seeding. This tantalizing possibility that life on Earth and any potential life on Mars may share a common origin, a shared genesis, is what makes the exploration of Mars so compelling. It has transformed the red planet from a mere object of astronomical curiosity into a target of immense geopolitical and philosophical importance. The upcoming Mars Sample Return mission is therefore not just another space probe. It is a high-stakes international endeavor to retrieve the one piece of evidence that could answer this question once and for all. By comparing the biology of Mars, if any exists, directly with our own, we could finally determine if we are part of the same family tree. Finding life on Mars that is biochemically identical to ours, using the same DNA, the same left-handed amino acids, would be a world-altering discovery, providing powerful, almost irrefutable evidence for panspermia. Conversely, finding nothing, or finding life that is truly alien in its fundamental chemistry, would suggest that life arose on Earth independently. Either way, the answer lies there, waiting in the red dust, holding the key to whether we are alone in our genesis or merely one branch of a family that began on a neighboring world.
The Earth-Mars connection remains the most studied and plausible pathway for life's exchange. The relentless push of solar system exploration has unveiled a portfolio of other, more exotic, and perhaps even more compelling locations. The first is our other neighbor, often dismissed as a lost cause, Venus. On the surface, it is Earth's evil twin, a true hellscape locked in a runaway greenhouse effect. Its atmosphere is a crushing 90 times thicker than Earth's, and surface temperatures are hot enough to melt lead, making it utterly inhospitable to life as we know it. Yet, this picture of a dead world has been dramatically challenged. High above the infernal surface, in the temperate cloud decks some 50 kilometers up, conditions are surprisingly gentle. Temperatures hover near room level, and atmospheric pressures are similar to those on Earth. For decades, visionary scientists like Carl Sagan have speculated that microbial life could persist in this aerial haven, floating on droplets of sulfuric acid. This once fringe idea exploded into the mainstream in 2020 with a controversial and highly debated report claiming the detection of phosphine gas in the Venusian clouds, a chemical that on Earth is overwhelmingly associated with biological processes. Though subsequent studies have cast significant doubt on the initial finding, the episode reignited intense global interest in Venus. It forced a strategic re-evaluation, recasting the planet's acid-laced clouds not necessarily as a permanent home for life, but as a potential temporary refuge, or even an atmospheric stopover point for microbes blasted from Earth or Mars, a stepping stone in the interplanetary network. But the true revolution in our search for life beyond Earth is happening far from the Sun, in the cold, dark realm of the gas giants. Here, hidden beneath colossal shells of ice, lie the most promising targets in the entire solar system, the ocean moons. Saturn's tiny moon Enceladus has transformed from an anonymous ball of ice into a primary target in the quest for our cosmic origins. In 2005, NASA's Cassini spacecraft made a stunning discovery. Massive geysers were erupting from deep cracks in the moon's southern pole, spraying vast plumes of water vapor and ice crystals hundreds of kilometers into space. This was undeniable proof of a liquid water ocean hidden beneath the ice. In a series of daring fly-throughs, Cassini's instruments tasted these plumes, and what they found was a scientific jackpot. The water was salty and rich in organic molecules. But the final, breathtaking discovery was the presence of sodium phosphates, an essential ingredient for DNA, RNA, and the energy-carrying molecule ATP, the very battery of life. Enceladus's hidden ocean is not sterile. It is a chemically rich, life-sustaining soup, a potential cradle for biology. For panspermia, the implications are twofold. First, it is a prime destination.
Any microbe-laden rock from the inner solar system that crashed there would find a welcoming, nutrient-rich environment. Second, and more profoundly, it is a potential source. Those powerful geysers are actively ejecting oceanic material into space, creating a constant stream of samples that could be captured by passing debris and transported elsewhere. Enceladus could be exporting its own brand of life across the solar system. Jupiter's moon Europa presents a similar, though more enigmatic case. Larger than Enceladus, its icy surface is scarred with cracks and streaks, hinting at a vast hidden ocean below that may contain more water than all of Earth's oceans combined.
A natural male narrator voice with a warm, friendly tone. Beneath that ice, scientists believe that interactions between the liquid water and the rocky seafloor could create hydrothermal vents, providing a steady source of energy and nutrients, perfectly mirroring the deep-sea ecosystems on Earth where life may have first begun. Like Enceladus, Europa is both a potential home for native life and a potential destination for cosmic seeds penetrating its icy shield. This has made these moons the new prime real estate in the solar system, shifting the geopolitical focus of space exploration beyond Mars and toward these tantalizing hidden oases. Finally, there is the true wild card of the outer solar system, Saturn's largest moon, Titan. It is a world utterly unlike any other, shrouded in a thick, nitrogen-rich atmosphere with clouds, lakes, and rivers. But these are not made of water. They are composed of liquid methane and ethane, existing in a deep freeze hundreds of degrees below zero. On its surface, complex organic molecules, known as tholins, form in the upper atmosphere and rain down, blanketing the landscape in a tar-like residue. While this frigid hydrocarbon world seems inhospitable to life as we know it, it is a magnificent prebiotic laboratory. It demonstrates on a planetary scale that the universe is hardwired to create complex organic chemistry even in the most exotic and alien environments. For panspermia, Titan's importance is therefore symbolic but profound. It proves that the building blocks for life are not a special feature of Earth-like worlds. They emerge spontaneously across a vast range of conditions, creating a galactic inventory of parts that could be incorporated into the great cycle of cosmic seeding and exchange, forever blurring the line between the living and the merely chemical. To truly comprehend the violent and profound opportunity for panspermia, we must rewind the clock 4 billion years to a time when the solar system was not the calm, predictable clockwork we see today. It was a place of breathtaking chaos, a cosmic shooting gallery on an unimaginable scale. In this primordial era, the orbits of the planets were still settling, and the space between them was thick with the leftover debris of their formation, a lethal swarm of asteroids and comets. Impacts were not rare, occasional events. They were a constant, defining feature of the environment. The colossal collision that tore a chunk from the nascent Earth to form our moon was merely the most dramatic of countless such cataclysms happening throughout the inner solar system. This relentless bombardment was not just destructive, it was the engine of a vast and continuous exchange of material. Earth, a young Mars, and a newly formed Venus were not the isolated islands we see them as today. They were nodes in a deeply interconnected network, a planetary archipelago linked by a constant barrage of impact ejecta. Sophisticated supercomputer models, which serve as our virtual time machines, have revealed that in the first few 100 million years of the solar system's history, billions upon billions of tons of rock were blasted from world to world. This vision transforms the story of life's origins. It shifts the narrative from one of isolated, independent sparks on separate worlds to a grander, more interconnected drama.
The early solar system was, in effect, a shared microbial ecosystem.
If life, or even just its complex chemical precursors, managed to gain a foothold on any one of these worlds, the constant exchange of material would have provided ample opportunity for it to spread to its neighbors. A successful origin on an early, water-rich Mars could have seeded a still-forming Earth, creating a single, extended family of biospheres, all sharing a common ancestry. Even in the absence of living organisms, the chemistry of life itself was in constant circulation. Amino acids, nucleobases, and other organic molecules delivered to the inner solar system by comets and asteroids would not have been confined to the planet they first struck. They would have been shared, blasted from world to world, enriching the prebiotic soup of each planet and increasing the odds that one of them would eventually cross the threshold into biology. The early solar system was a crucible, a violent but profoundly generative environment where the lines between worlds were blurred and the raw materials for life were part of a shared circulating inventory. In this chaotic, high-stakes environment, timing was everything. For panspermia to be a successful genesis strategy, the exchange of material must align perfectly with the emergence of habitable conditions. There had to be a window of opportunity where the traffic of cosmic couriers was at its peak, just as the destination worlds were becoming receptive to their cargo. And the evidence suggests that just such a perfect alignment occurred. The period of the most intense bombardment, known as the Late Heavy Bombardment, happened precisely as the planets were cooling from their molten formation. Oceans were beginning to condense on their surfaces, and primordial atmospheres were starting to stabilize. It was a moment of extraordinary cosmic synchronicity. The overall mempacks that posed an existential threat to emerging life were also the delivery mechanism for its potential seeds. If life had managed to begin on one world just slightly earlier than its neighbors, perhaps on Mars, which is smaller and cooled more quickly, its export to a waiting Earth could have been incredibly rapid and efficient. Today, the solar system has grown quiet. The celestial shooting gallery has largely closed down. Impacts are now rare. The vast distances between planets are more stable, and the dynamical highways are less trafficked. The window for frequent, large-scale seeding has, for the most part, closed. But 4 billion years ago, the timing may have been absolutely perfect. It was a brief but critical epoch of intense activity that occurred at exactly the moment when the terrestrial worlds were ready to receive and nurture the fragile beginnings of biology. This was not just a random series of events. It was a delicate and violent dance between destruction and creation, a race against time where the delivery of life seeds had to occur before the delivery routes themselves faded into the quiet stability of the mature solar system we inhabit today. The question is not just whether life could travel between worlds, but whether it arrived during that fleeting, chaotic, and uniquely perfect moment in our shared history. When we apply this rigorous quantitative lens to panspermia, the sheer scale of the numbers can be paralyzing. The distances are measured in millions of kilometers, the timescales in billions of years, and the probabilities seem vanishingly small. To break this intellectual gridlock, scientists often turn to a powerful tool for navigating extreme uncertainty, the Fermi-style estimate. Named after the physicist Enrico Fermi, who was legendary for his ability to make remarkably accurate calculations with very little data, this method involves breaking a vast, complex problem down into a series of smaller, more manageable steps. By estimating each step, even crudely, one can arrive at an order of magnitude answer that reveals whether a hypothesis is plausible or absurd. When we apply this rigorous quantitative lens to panspermia, the theory moves from the realm of philosophical fancy into the cold, hard domain of statistical probability. It becomes a numbers game, a cosmic lottery played out over geological time.
Let's begin with the first variable: how many potential couriers are launched? We know from cratering records on the Moon and other planets that large sterilizing-level impacts on worlds like Earth and Mars have occurred countless times over the past 4 billion years. Each of these cataclysmic events is capable of ejecting billions of kilograms of crustal material into space. State-of-the-art simulations run on government supercomputers suggest that from Mars alone, millions of individual rocks, ranging in size from small pebbles to massive boulders tens of meters across, have been successfully flung into interplanetary orbits. This is the first staggering number in our calculation, the sheer quantity of lottery tickets being generated. Next, we must ask how many of these ejected fragments actually make it to a viable destination.
The overall mood of the solar system's dynamical highways comes into play. Not every rock launched from Mars is destined to reach Earth. Most will be flung into the Sun, ejected from the solar system, or captured by the gravitational pull of another planet like Jupiter. However, the models indicate that a surprisingly high percentage, roughly 1 in 100, are eventually steered into an orbit that intersects with Earth. This still leaves us with tens of thousands of potential couriers from every single major impact event, a massive number of potential deliveries. Of those that reach Earth, how many survive the final fiery plunge and land softly enough to deliver a viable biological cargo without sterilizing it on impact? Here, the odds narrow dramatically. Perhaps only a tiny fraction, a handful from each event, successfully complete this final stage. But this is where the power of geological time becomes the decisive factor. These impacts are not one-time events. They repeat again and again over the immense 4 billion-year history of our solar system. Even if only a minuscule fraction of all ejected rocks, say 1 in a million, successfully navigates the entire journey and carries a viable microbial payload, the cumulative number of attempts becomes astronomically large. Over billions of years, with thousands of major impacts, the universe has taken this shot millions, perhaps billions of times. Panspermia does not need to work often. It only needs to have worked once. A single successful delivery, one microscopic Adam or Eve arriving in the fertile oceans of a young Earth, would be enough to change the course of planetary history forever. The gap between ejection and arrival is therefore defined by one factor above all others: time. The overall mood of panspermia is the ultimate arbiter, determining whether biological survival is plausible or a statistical impossibility. Computer models show a vast distribution in these travel times. Some rocks wander the void for tens of millions of years before finding a home, a journey so long that any biological material would be eroded to nothing by cosmic rays. This is the grim average case. But what matters most for panspermia is not the average, but the exceptions, the tail end of the distribution. The same models show that some ejecta can reach Earth with incredible speed in as little as 20 years. Others might take a few thousand. Now we must weigh this cosmic timetable against the harsh realities of biology's own internal clock. Dormant spores are not immortal. They degrade slowly, but they are not immune to the relentless laws of chemistry and physics. Radiation damage accumulates, and even without it, the complex molecules of life spontaneously break down over time. A common estimate for the half-life of DNA, even under ideal cold and dry conditions, is around 500,000 years. After 1 million years, most genomes would be little more than unrecognizable fragments. This is biology's shelf life. And yet, this is where the two sets of statistics create a stunning window of opportunity. The existence of those rare, rapid transfers, journeys lasting under a century, is a physical reality of celestial mechanics.
And the survival of hardy microbes over such a time frame is a biological plausibility. This sliver of overlap between the fastest cosmic journeys and the outer limits of biological endurance is where the entire hypothesis of lithopanspermia lives or dies. Life does not need to survive every journey, or even most of them. It only needs to get lucky just once. A natural male narrator with a warm, friendly tone. Time is a filter of brutal efficiency, but it is not an absolute barrier. Even if a microbe is fortunate enough to be launched within a protective rock and catch a ride on a rapid cosmic highway, the journey is far from guaranteed. The transit is a relentless gauntlet, a multi-stage process of elimination, where survival depends on overcoming three fundamental choke points. Three distinct lethal threats that work in concert to erode and destroy biology over time. Even within the relative safety of a stone sarcophagus, these forces are at play, each imposing its own deadline on the traveler's viability. The first and most immediate of these is ultraviolet radiation. While the rock shield can block the worst of it, any microbe near the surface or in a microscopic crack that gets exposed to direct sunlight would be sterilized almost instantly. UV light acts as a swift and brutal executioner, slicing through the delicate bonds of DNA in seconds. Shielding is not just an advantage, it is an absolute non-negotiable requirement for survival. The second choke point is more subtle, but equally deadly: desiccation. The hard vacuum of space is the most perfect desert imaginable, a place of zero pressure that aggressively rips water molecules from any substance. For a living cell, this is catastrophic. Water provides the medium for all biochemical reactions and gives the cell its structural integrity. As it evaporates, the cell becomes brittle, its membranes shatter, and its internal machinery grinds to a halt. While spores are masters of controlled drying, deliberately packing their DNA with protective proteins to stabilize its structure against this very threat, the process is not perfect. Over thousands of years, the relentless vacuum can cause microscopic fractures to form and propagate, slowly turning the once viable organism into a desiccated, lifeless husk. The third and most insidious choke point is the one against which there is no shield: spontaneous chemical decay. This is the slow, inexorable march of entropy, the fundamental law of the universe that dictates that all complex systems will eventually break down. Even in the frozen, radiation-free dark, the complex molecules of life are not immortal. Chemical bonds will slowly, randomly break apart. Nucleobases will mutate. The elegant, information-rich structure of DNA will unravel. This process is glacially slow, but over the timescales of an interplanetary journey, it is a relentless and unavoidable threat. Even without a single cosmic ray strike, biology simply has a shelf life. Together, these three choke points form a tripartite trial. They ensure that for panspermia to succeed, it requires a perfect alignment of circumstances. A microbe needs not only a thick shield to protect it from radiation and desiccation, but also a rapid transit to ensure it arrives before its own internal clock runs out. Without both, even the hardiest spore will eventually succumb to the unforgiving physics of the cosmos. But let us assume that a traveler beats these astronomical odds. It survives the launch, the transit, and the fiery re-entry. The journey is still not over. Reaching a planet is not the end of the story. It is merely the beginning of the final and perhaps most difficult test. The vast majority of rocks that cross Earth's orbit will never strike the planet at all, burning up harmlessly in the atmosphere or sailing past into the void. Those that do land face yet another filter: the conditions upon impact. A violent crash can vaporize the meteorite and sterilize its entire biological payload. Only the smaller fragments that land gently in a receptive environment, like an ocean or a shallow pond, offer a real chance for the successful delivery of their cargo. And even then, what happens next? For panspermia to matter, life must not only survive the journey, it must thrive upon arrival. The landing site must be chemically and physically compatible, not too acidic, not too salty, not too dry. A few viable spores landing in the sterile, primordial oceans of a young Earth would have found a world of opportunity. But those same spores landing on the cold, arid, and irradiated surface of modern Mars would likely face a swift and silent death. This final, speculative stage is known as post-landing recovery and colonization, and it is the ultimate bottleneck. A handful of cells might survive the trip, but unless they can reawaken their metabolism, find nutrients, and begin to reproduce before their own internal damage overwhelms them, their epic journey ends in a quiet, microscopic failure. Successful panspermia is not just about survival, it is about establishing a beachhead. Ultimately, the entire hypothesis of panspermia exists in the tense, uncertain space between our most sophisticated computer models and our most audacious laboratory experiments. The models tell us that the exchange of rocks between worlds like Earth and Mars is not a rare event, but a geological certainty. They show that some of these journeys can be short enough to potentially preserve biology. The experiments, in turn, tell us that the hardiest forms of life are astonishingly resilient. They show that spores can survive the crushing shock of launch, the vacuum of space, and the inferno of re-entry.
Each line of evidence, on its own, provides a compelling piece of the puzzle. What we cannot yet do is test the entire causal chain at once. No experiment has ever followed a real rock carrying real microbes on a multi-year journey across interplanetary space and back again. Until that day comes, panspermia will remain one of science's greatest unresolved narratives, a hypothesis stitched together from powerful but partial evidence. The models suggest it could work. The experiments suggest biology is tough enough. Whether the two ever aligned in reality, in the deep past of our solar system, remains one of the most profound and tantalizing open questions in all of science. Beyond the mere presence of organic molecules, the chemistry of the cosmos holds a deeper, more enigmatic secret. A subtle, almost ghostly fingerprint that hints at a profound connection between the inanimate universe and the machinery of life. This is the mystery of homochirality, one of the most stubborn and revealing puzzles in the entire field of astrobiology. To understand it, one must grasp a fundamental quirk of life's molecular architecture. The amino acids that build our proteins are not symmetrical. Like our hands, they exist in two mirror image forms, a left-handed L version and a right-handed D version. In any non-biological chemical reaction, a laboratory soup of amino acids will always produce a perfectly random 50-50 mix of both forms. Yet, for reasons that are still not fully understood, all life on Earth is built with an almost absolute dictatorial preference for the left-handed version. This is a universal signature, a chemical standard that holds true from the simplest bacterium to the most complex mammal. Why this bias exists is a question that cuts to the very heart of life's origins. If life began in a random primordial soup, why would it choose one hand over the other? For decades, this was seen as a purely terrestrial mystery, a choice made by Earth's earliest life forms that became locked in through evolution. But the meteorites tell a different, more cosmic story. When scientists performed a detailed analysis of the amino acids within the Murchison meteorite, they found something that defied conventional chemistry. A small but consistent and measurable excess of the left-handed L form, the same form preferred by life.
The imbalance was subtle, only a few percent, not the near total dominance we see in biology, but it was undeniably there. This was a watershed moment. It suggested that the bias toward left-handedness was not invented on Earth. It was inherited from space. Some process occurring in the deep, cold interstellar clouds or on the surface of the meteorite's parent asteroid billions of years ago had already tilted the odds in favor of one hand. The leading theory is that polarized starlight could have selectively destroyed one form of the molecules while leaving the other intact, creating a slight imbalance that was then delivered to a young Earth. If this is true, then our planet may have been seeded not with a random 50-50 mix of ingredients, but with a pre-bias toolkit, a starter set that already contained the chemical preference that all subsequent life would adopt. Once life began, the process of natural selection would have amplified this small initial bias into the absolute commitment we see today. The meteorite data does not solve the mystery of homochirality, but it powerfully relocates it. It suggests the phenomenon is not an exclusively terrestrial trait, but a cosmic one, faintly written into the very chemistry of the universe itself. This idea of a chemical inheritance is further reinforced by another powerful forensic tool, isotopes. Isotopes are different versions of an element that have the same number of protons but a different number of neutrons, giving them slightly different masses. The ratio between these heavy and light isotopes acts like a unique chemical passport, a fingerprint that can reveal where and how a molecule was formed. Biological processes on Earth, for instance, tend to show a slight preference for lighter isotopes, leaving a detectable signature in the carbon, nitrogen, and hydrogen ratios of organic matter. When we analyze the isotopic ratios in the organic molecules found within meteorites, we often find signatures that are utterly alien to anything on Earth. They show enrichments in heavy isotopes like carbon-13 or deuterium, heavy hydrogen, which are characteristic of chemical reactions that occur in the extreme cold of interstellar space or the primitive solar nebula. These are not just different, they are provably non-terrestrial. When we find an amino acid in a meteorite with a weird isotopic signature, we know with absolute certainty that it is not a stray piece of earthly contamination. We are looking at a molecule that is older than our planet, a chemical traveler that journeyed vast distances before being delivered here. In this way, isotopes serve as the ultimate, incorruptible witnesses. They are tiny, immutable markers that prove the ingredients for life carry within them the story of their own cosmic migration, a testament to a time when the chemistry of our world was being written by the stars. The discovery of biased extraterrestrial amino acids was a profound revelation, but it was only the opening act in a much larger chemical drama. While proteins are the workhorses of biology, life as we know it requires a far more sophisticated and diverse toolkit. It needs a way to store information, a system to transfer energy, and a structure to contain its operations. This meant scientists had to hunt for the other, even more elusive pillars of biology, the sugars and nucleobases that form the backbone and rungs of RNA and DNA, and the phosphates that power metabolism and build cell membranes. For decades, these molecules seemed to be uniquely terrestrial achievements, the products of Earth-specific primordial chemistry. Their apparent absence in meteorites led many to believe that while space could provide the simple bricks for life, the complex architectural plans had to be drawn up here at home. This perceived gap became a critical firewall in the panspermia debate. But this firewall was about to be systematically dismantled by a new generation of high-stakes robotic explorers. The problem, as always, was contamination. The hunt for these delicate molecules in fallen meteorites was a scientific minefield haunted by the constant risk that any detection was simply the result of earthly microbes. To get a definitive answer, humanity had to do something unprecedented. It had to leave Earth, travel hundreds of millions of kilometers to a primitive, untouched world, and bring a piece of it back. This imperative launched a new, quieter, but intensely competitive space race, not for the moon, but for the chemical secrets locked inside the solar system's most ancient asteroids. Japan's Hayabusa 2 mission was a triumph of precision engineering and national ambition. Its target, the asteroid Ryugu, was a time capsule from the dawn of the solar system. The pristine samples it returned in 2020 were more than just space rocks. They were the answer to a prayer. It confirmed that a key ingredient for life's biochemistry was not just locked away in ancient rocks, but was present, dissolved, and chemically available in a vast liquid water ocean right now, on a world hundreds of millions of kilometers from Earth. Taken together, these three discoveries, uracil on Ryugu, phosphates on Bennu, and dissolved phosphates in the oceans of Enceladus, represent a fundamental paradigm shift in our understanding of the universe's potential for life. They sketch a cosmos that is not just incidentally sprinkled with a few simple organics, but one that is systematically preloaded with the entire chemical toolkit for biology. Sugars, nucleobases, and phosphates are not rare, miraculous accidents of Earth's chemistry. They are recurring, standard outcomes of the natural processes that govern the formation of planets, asteroids, and moons. The ingredients for life are not confined to our world. They are, it seems, everywhere, scattered like seeds across the solar system, just waiting for the right conditions to assemble and awaken. In any scientific endeavor with stakes as high as the origin of life, the path to discovery is never a straight line. It is a treacherous landscape, littered with false positives, seductive mirages, and cautionary tales. The very grandeur of the panspermia hypothesis acts as a powerful magnet, attracting not only rigorous, methodical science, but also sensational claims that ignite the public imagination before collapsing under the cold, hard light of scrutiny. The history of this field is therefore a history of both bold ideas and crucial errors. These are not failures, but the essential, self-correcting mechanism of science at work. A planetary immune system that must identify and neutralize flawed evidence to protect the integrity of the search.
The overall mood should be relaxed, engaging, and comfortable to follow, like a light science podcast. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tempo should be around 0.8. Two specific episodes stand as monumental pillars of this cautionary principle, powerful case studies in how easily the desire to find life beyond Earth can lead us astray. The first is the story of a rock from Mars that promised to change the world. In 1984, a team of geologists found an unremarkable-looking meteorite on the pristine ice of Antarctica's Allan Hills. Catalogued as ALH8401, it was later identified as one of the oldest known rocks from Mars, blasted from its surface by an ancient impact millions of years ago. For over a decade, it remained a scientific curiosity. Then, in 1996, it became the most famous rock on Earth. A team of NASA scientists, after years of painstaking analysis, held a global press conference to announce a shocking possibility. Peering deep inside the meteorite with powerful electron microscopes, they had found tiny, worm-like structures that they interpreted as the possible fossilized remains of Martian microbes. The evidence seemed compelling. The shapes were suggestive, and they were found alongside complex organic molecules and mineral grains often associated with biological activity.
The announcement was an absolute bombshell, a political and cultural event that transcended science. The President of the United States made a televised address from the White House lawn. It seemed for a breathtaking moment that humanity had finally found evidence that we were not alone. But almost as quickly as the excitement erupted, the scientific counterattack began. A global army of skeptics descended upon the data, and the case began to unravel. Critics pointed out that the supposed nanofossils were hundreds of times smaller than the smallest known bacteria on Earth, questioning whether they were large enough to contain the necessary machinery for life. Other researchers demonstrated that every single piece of supporting evidence, the organic molecules, the magnetite crystals, could have been formed by completely non-biological geological processes. Gradually but decisively, the scientific consensus shifted. The evidence was not a smoking gun. It was an inkblot test, an ambiguous set of shapes into which the profound human desire to find life had been projected. The ALH 84001 episode remains the ultimate cautionary tale in astrobiology. It teaches a hard lesson about the seduction of morphology. Our eyes and brains are hardwired to see patterns and life even where none exists. Without irrefutable, independent lines of chemical and isotopic evidence, suggestive shapes in rocks are not proof. They are merely geology's ghosts. A second, stranger, and more recent cautionary tale unfolded not in a sterile NASA laboratory, but under the monsoon skies of India. In the summer of 2001, a bizarre and unsettling phenomenon occurred across the southern state of Kerala. Following reports of a sonic boom from a suspected meteor airburst, downpours of crimson-colored water began to fall, staining clothes, buildings, and rivers a startling blood-like red. The red rain of Kerala sparked widespread fear and wonder. While initial scientific assessments pointed toward atmospheric dust or pollution, a small group of researchers proposed a far more provocative extraterrestrial explanation. They argued that the red particles in the rain were not of this Earth, but were alien microbial cells delivered by a comet fragment that had disintegrated in the upper atmosphere. A literal, ongoing rain of life from space, a dramatic confirmation of panspermia in action. The story captured the global media's attention, becoming a modern-day myth. However, rigorous subsequent analysis provided a far more mundane, though equally fascinating explanation.
The red particles were identified conclusively as the airborne spores of a local species of terrestrial green alga, Trentipolia annulata, whose biology allowed it to thrive in the atmosphere and whose potent red carotenoid pigments had colored the rain. The Kerala red rain stands as a different but equally important lesson. The strange is not the same as the extraterrestrial. Nature, here on our own planet, is capable of producing phenomena so bizarre and unexpected that it is easy to mistake them for something alien. Both of these episodes underscore a crucial, non-negotiable principle. In the search for life beyond Earth, our standards for evidence must be ruthlessly high. Extraordinary claims require not just extraordinary evidence, but an extraordinary discipline in how that evidence is gathered, tested, and interpreted, ensuring that when the day of discovery finally comes, it is not another ghost in the rock, but the unambiguous, undeniable truth. In the grand, speculative theater of panspermia, there exists a final, deeply unsettling act, a concept so provocative it straddles the line between science, philosophy, and geopolitical strategy. It is the idea of directed panspermia.
In 1973, in a move that shocked the scientific establishment, Francis Crick, the Nobel laureate who co-discovered the very structure of DNA, and the brilliant biochemist Leslie Orgel published a paper that asked a question of almost unimaginable audacity. What if life on Earth was not an accident at all? What if it was a deliberate act, an intentional seeding of our young, sterile world by a distant and ancient extraterrestrial civilization? This was not a theory of flying saucers or alien visitations in the popular sense. Crick and Orgel envisioned something far more subtle and patient. An advanced civilization, perhaps facing its own mortality or driven by a philosophical imperative, launching unmanned probes laden with hardy, dormant microbes, sending them like interstellar message-in-a-bottles toward promising, nascent planetary systems. Earth, they speculated, could have been one such target, our entire biosphere the result of a single successful delivery billions of years ago. At the time, the paper was treated largely as a fascinating but ultimately untestable thought experiment, a way of challenging the scientific community's core assumptions about the inevitability of abiogenesis on Earth. For decades, it remained on the farthest fringes of academic thought. But in a stunning turn of events, the relentless march of our own technology has dragged this fanciful idea out of the fringe and into the harsh light of imminent reality. The concept of seeding life is no longer hypothetical because humanity itself is standing on the precipice of being able to do it.
The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The overall tempo should be around 0.8. We have already launched spacecraft, the Voyager probes, that have left our solar system and are now traveling through interstellar space. We are actively developing technologies like CRISPR that allow us to engineer microbes with enhanced resilience, custom-tailored for survival in extreme environments. International projects like Breakthrough Starshot are designing and prototyping the very laser-propelled nanocraft that could one day travel to nearby star systems. The chilling truth is this: if we so chose, humanity could, within the next few centuries, design and launch its own directed panspermia missions, dispersing Earth life across the cosmos. This new reality transforms the entire debate. The question is no longer just, did it happen to us, but has now become a far more urgent and terrifying ethical question. Should we do it? The very fact that we can now seriously contemplate this act forces us to confront the profound ethical and geopolitical questions it raises. The argument for directed panspermia is born from a sense of existential urgency and moral duty. Life, as far as we know, is the most precious and fragile phenomenon in the universe, confined to a single, vulnerable planet. Our world is a cosmic bullseye, subject to asteroid impacts, supervolcanoes, and the eventual, inevitable expansion of our own sun into a red giant that will one day sterilize the biosphere. In the face of this cosmic certainty, some argue that we have a moral obligation, a sacred duty, to act as life's custodians and ensure its survival by spreading it beyond the cradle of Earth. It is a cosmic lifeboat strategy. Seeding other worlds would be the ultimate act of preservation, ensuring that the legacy of 4 billion years of evolution continues long after our own planet is gone. From this perspective, it is an act of creation, a way of giving the universe more voices, of transforming countless sterile oceans on distant exoplanets into vibrant, living ecosystems. But the case against is equally, if not more, powerful, and it is rooted in a deep-seated fear of our own ignorance and hubris. The first and most critical objection is the principle of non-interference, what science fiction has termed the prime directive.
If a world we target for seeding already harbors its own native microbial life, a unique and independent genesis, then introducing robust Earth microbes could trigger an ecological apocalypse. Our seeds could become an invasive plague, outcompeting and exterminating a native biology before we ever had the chance to discover it. We would, in our attempt to create, become destroyers, erasing a unique chapter in the cosmic story. Secondly, there is the profound ethical issue of hubris. We have a vanishingly poor understanding of the complex interplay of our own planet's ecosystems, which we are actively destroying. Yet directed panspermia assumes we have the wisdom to engineer the biospheres of other worlds. The law of unintended consequences operates on a planetary scale, and the results of our meddling would be unknowable and irreversible. For many, this is not an act of creation, but one of cosmic colonialism, imposing our specific terrestrial biology onto other worlds without their consent, expanding our influence not through curiosity, but through a dangerous and arrogant presumption that our brand of life is the only one that matters. The question of whether we should seed the stars is therefore no longer a parlor game for philosophers. A natural male narrator with a warm, friendly tone. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The overall tempo should be around 0.8. It is rapidly becoming one of the most significant policy decisions our species will ever have to make, a choice that will define our cosmic legacy as either creators or contaminants. One of the foundational strengths of the scientific method, the very principle that separates it from faith and philosophy, is that its ideas must be testable. A hypothesis, no matter how elegant or compelling, must make concrete, falsifiable predictions about the world. For centuries, the debate between panspermia and abiogenesis was largely a philosophical one, relegated to the realm of abstract speculation. But today, as we stand on the cusp of retrieving samples from other worlds, this ancient question has finally entered the laboratory. The two competing theories are no longer just stories. They are rival scientific models that make starkly different and directly testable predictions. By examining these predictions, we can now design the very experiments that could, within our lifetime, finally distinguish between them and provide a verdict on our cosmic origin story. First, let's consider the predictions made by abiogenesis, the theory that life began independently on this planet, a homegrown phenomenon born from Earth's unique primordial chemistry. If this is true, then life here should represent a unique, one-off solution to a universal problem. Its fundamental biochemistry would be the result of a specific set of environmental conditions and random chemical events that occurred on the early Earth. Therefore, the theory predicts that if we discover life elsewhere in the solar system, it should be truly and profoundly alien in its chemical architecture. It might not use DNA or RNA as its genetic molecule, but an entirely different information-carrying polymer, a xenonucleic acid. The overall mood is not just capable of creating life, but that it is practically teeming with it, a cosmos where biology is a common outcome of planetary evolution. Panspermia makes the exact opposite prediction. If life is a cosmic traveler that has spread from world to world, then we should not expect to find radical difference, but profound continuity. If life on Mars exists and shares a common ancestor with us, it should look eerily, uncannily familiar at the molecular level. It should use the same DNA-RNA information system, employ a similar genetic code to translate that information into proteins, and be built from the same set of left-handed amino acids. Its core cellular machinery, the ribosomes and enzymes that power life, should show clear signs of a shared ancestry with our own. Finding life on Mars that is biochemically compatible with ours would be the ultimate smoking gun for panspermia. It would mean our family tree has a branch on another world. In this sense, the universe itself has set up the decisive experiment. The first time we analyze a truly alien microbe will be the moment of truth. An organism that is familiar argues for panspermia. An organism that is alien argues for multiple, independent origins. To conduct this ultimate biological comparison, scientists have identified 3 key, unambiguous markers that could definitively establish a familial link. The first is the genetic code, the set of rules that translates the sequence of letters in DNA and RNA into the sequence of amino acids in a protein. On Earth, this code is nearly universal, a shared language spoken by every living thing, from the simplest bacterium to a blue whale. If we were to discover Martian microbes that use the exact same code, the probability of that occurring by sheer coincidence on 2 separate worlds is statistically infinitesimal. It would be the cosmic equivalent of finding 2 isolated, uncontacted civilizations on opposite sides of the galaxy that independently developed the English language, down to the last nuance of grammar and syntax. It would be powerful, near-certain proof of a common ancestry. The second marker is molecular chirality. As we've seen, Earth life's exclusive use of left-handed amino acids and right-handed sugars is a deep and mysterious signature. If extraterrestrial life shares this exact same asymmetry, it strongly suggests inheritance from a common pre-biased source. But if Martian microbes were to use the opposite hand, or perhaps more interestingly, a random mix of both, it would be a clear signal of an independent origin, a separate roll of the chemical dice. Finally, the most definitive test would come from phylogenetics, the science of constructing evolutionary trees. If we could sequence the genetic material of a Martian organism, we could compare it to the entire database of life on Earth. We could determine whether the Martian life forms a new, separate branch within Earth's great tree of life, proving it is a long-lost cousin, or if it forms an entirely separate second tree of life, a truly independent genesis. This comparative biology offers a clear and powerful path forward. The overall mood of science today will not only tell us if we are alone, but whether the story of life is a single, epic novel that spans the cosmos, or a library of countless different books, each with its own unique beginning. The grand cosmic jury is now being assembled. The era of purely theoretical debate is over, and we are entering a new, high-stakes phase of active investigation, a time of robotic couriers and interplanetary forensics. The verdict on panspermia will not be found in philosophical arguments, but in the sterile, high-security laboratories of Earth, analyzing physical evidence brought back from the far reaches of the solar system. The most direct way to test the hypothesis is to examine the delivery vehicles themselves. For over a century, our only access to this material was through the random lottery of meteorite falls. While invaluable, these samples were always tainted, their scientific integrity compromised by their passage through our own biosphere. But today, we no longer have to wait for the messengers to come to us. We go to them. The successful sample return missions to the asteroids Ryugu and Bennu represent a strategic and technological quantum leap. By collecting pristine, untouched material and returning it in sealed capsules, they have provided an unblemished look at the chemistry of the early solar system. The discovery of uracil, niacin, and phosphates in these samples has already confirmed that the cosmic inventory for life is far richer than we ever dared to hope. Each future mission will refine this picture, probing deeper to see just how far this prebiotic chemistry goes, and whether it ever crosses the final fateful line into biology. A parallel line of investigation involves the comets, those icy wanderers from the solar system's outer darkness.
The European Space Agency's historic Rosetta mission, which orbited and landed on Comet 67P, sniffed a veritable zoo of organic molecules in its coma, including the amino acid glycine. This confirmed that comets, like asteroids, are vast storehouses of life's building blocks. A future sample return mission to a cometary nucleus, retrieving a core of its ancient frozen ices, could provide the ultimate ground truth, settling once and for all whether these bodies preserve chemistry that closely approaches biochemistry. And then there is the ultimate prize, the holy grail of this entire field of inquiry, the interception of an interstellar visitor. The flybys of Oumuamua and Borisov proved that material from other star systems is actively drifting through our own. While we could only watch as they passed, the next great leap in space exploration will be the development of rapid response missions, robotic interceptors capable of chasing down these travelers and sampling them directly. If we were to one day find complex prebiotic chemistry, or, in the most world-altering scenario imaginable, actual biological material on a rock that we know came from another star, it would provide the clearest and most profound evidence yet that panspermia is not just a local phenomenon, but a truly galactic process, weaving the web of life between the stars. But in the near term, all eyes and a significant portion of the world's space exploration budgets are focused on a single monumental target: Mars. The red planet is central to the entire panspermia debate, the one place where a shared genesis with Earth is a direct, plausible possibility. That is why the upcoming multi-billion-dollar multinational Mars sample return mission is arguably the most critical and ambitious scientific undertaking of the 21st century.
The overall mission of almost unimaginable complexity, a multi-stage robotic relay race to bring the first pristine samples of Martian rock and soil back to Earth. The scientific and geopolitical stakes are astronomical. The challenges are twofold, each representing an unprecedented technological hurdle. The first is absolute containment. To preserve the scientific integrity of the samples, they must remain untouched by a single molecule of Earth's biology. This requires the design of sterile handling facilities with a level of stringency that makes a hospital operating room look like a swamp. Clean rooms within clean rooms, all handled by robotic arms to prevent any human contact. Simultaneously, we must prevent back contamination, the remote but catastrophic possibility of introducing a Martian microbe into Earth's biosphere. The second challenge is the burden of proof. The biosignatures found within the rocks must be utterly unambiguous. The lesson of ALH 84001 was learned in the harshest way possible. Cell-like shapes are not enough. The scientific teams will be hunting for a convergence of evidence, complex organic molecules with a clear biological pattern, isotopic ratios that favor life, and perhaps even the remnant fragments of genetic material. Every potential signature must be rigorously tested against any possible non-biological explanation. The results of the MSR mission, expected in the next decade, will be transformative, regardless of the outcome. If the Martian samples reveal biology that is biochemically similar to our own, it will provide the most powerful evidence to date in support of panspermia. If they reveal a biology that is utterly different, it will be a triumph for abiogenesis, proving a second independent genesis in our solar system. And if they reveal nothing at all, it will deepen the profound mystery of why Earth succeeded where its sibling world failed.
In this scenario, the Mars Sample Return mission stands as one of the most direct, falsifiable tests of life's potential spread ever conceived. A single mission that could forever alter our understanding of our place in the universe. Beyond the Martian dust and the icy plumes of the outer solar system, a final, more intimate test of panspermia may lie hidden within our own biology. If life on Earth was seeded from a common interstellar source, it is possible that our own planet was not the only recipient. The galaxy could be filled with countless cousin biospheres, each born from the same ancestral seed but evolving down radically different paths, shaped by the unique pressures of their own worlds. In this scenario, the fundamental building blocks of life, the DNA, the amino acids, would be the same everywhere, a universal standard. But the organisms they build would be fantastically diverse. If we were to ever encounter such life, it would be a moment of profound recognition and dizzying strangeness, like meeting a relative from a lost branch of the family who has become someone completely unrecognizable. The search for extraterrestrial intelligence, SETI, is, in this context, more than a search for alien minds. It is a search for shared biology, a hunt for a galactic echo of our own molecular makeup. The ultimate implication of panspermia, if proven true, would be a final and decisive reframing of humanity's place in the universe. It would represent the last step in the great Copernican demotion. First, we learned that the Earth was not the center of the solar system. Then, we learned our Sun was just one of billions in a vast galaxy, which itself is one of trillions. Inside the sealed capsule, scientists found not only a rich diversity of amino acids, but for the first time, irrefutable proof of uracil, one of the 4 nucleobases of RNA. Alongside it was niacin, or vitamin B3, a compound absolutely essential for the metabolic processes that provide energy to all living cells. This was a 1-2 punch to the theory of Earth's chemical exceptionalism. The universe wasn't just making the bricks, amino acids, it was manufacturing the genetic alphabet to write the instructions, uracil, and the battery packs to power the machinery. NASA's OSIRIS-REx mission to the asteroid Bennu delivered the next stunning blow. The samples it returned in 2023 contained another surprise, a piece of the puzzle that many scientists believed might be the ultimate bottleneck for life in the cosmos: phosphates. Phosphorus is the backbone of life's information system, forming the structural scaffolding of both DNA and RNA. It is the core component of ATP, the universal energy currency of the cell. Many models of planetary habitability had assumed that while carbon might be plentiful, accessible phosphorus would be incredibly scarce on other worlds. Bennu proved that assumption wrong. The pristine asteroid rubble contained abundant, readily available magnesium-sodium phosphates, demonstrating that this most critical and supposedly rare ingredient is a standard component of primitive bodies in our solar system. But perhaps the most dramatic discovery of all came from a mission not designed to return a sample, but to taste the oceans of a distant moon. Far out in the Saturnian system, the Cassini spacecraft flew directly through the icy plumes erupting from Enceladus. Its instruments detected not only organic molecules, but also high concentrations of sodium phosphates dissolved in the plume particles. This was a game-changing find. And so, as this investigation concludes, we are left with this deep and generous wonder. The cosmos is not a barren, hostile emptiness, but a fertile ground, restless with creative chemistry. Meteorites fall, carrying the building blocks of proteins. Asteroids are confirmed to hold the alphabet of our genes and the batteries for our metabolism. Distant ocean moons vent geysers filled with the very salts and organics that could fuel a new genesis. Everywhere we look, we find the stage being set for life.
The universe seems predisposed to complexity, constantly experimenting in a billion different crucibles, pushing matter to self-organize and grow. Whether these processes ultimately culminate in biology depends on local conditions, but the raw potential is undeniably, universally present. Let us, for a final moment, step back and see this story as a whole. Picture a single grain of dust, adrift in the cold, silent dark between the stars. It is infinitesimally small, a mote of apparent insignificance. Yet it carries within it the seed of something astonishing. On its frozen surface, the gentle, persistent light of distant stars rearranges simple molecules, forging the first amino acids. Over millions of years, it joins with countless others, drawn together by gravity to form the nucleus of a comet or asteroid. This body, a dirty snowball carrying a precious cargo, then embarks on a long, looping journey through a nascent solar system, a journey that ends in a fiery collision with a young, molten world. The impact delivers the chemistry that will tip the scales, seeding the planet's cooling oceans with the potential for life. From that dust and that rock and that water, a long, unbroken chain of replication and evolution begins. A chain that, after 4 billion years of patience, resilience, and the quiet creativity of the cosmos, leads directly to you. In you, the universe has found a way to become conscious, a way to ask the very questions that haunt our existence. Are we the children of this earth, or are we the children of the stars? Do our cousins await us on distant worlds, or are we one of many lonely beginnings scattered like spores across the vastness of space and time? The answers are coming. They lie sealed in the sample tubes on Mars. They are streaming through the plumes of Enceladus, and they are waiting in the next interstellar messenger that will silently drift through our skies. For now, we can only look up, knowing that whether we were seeded from beyond or born of this world alone, we are an integral part of a universe that is endlessly and beautifully fertile with possibility.